Today we will begin looking at the derivative of a composite function. To begin, one may ask, well, what is a composite function? So a composite function is a function made up of other functions. So let's just look at an example here. Now, is this a composite function? F at x equals 3x minus 5 to the power of 4. Now, is that a composite function? You look at this and you think to yourself, is this made up of more than one function? To the eye, you may think at first, no, this is just one function. But if you recall back in advanced functions, when we looked at functions where f was following g of x, where g of x was following h of x, whichever the case might be, we would know that this could be made up of more than one function. So yes, this is a composite function. Now, still you might be wondering, but how? How is this a composite function? Well, what I could do is I could say, since this is f at x, I'm going to use my two composite functions to make up this composite function, as g of x and h of x. So let's say g of x is our inside term, so 3x minus 5. And therefore h of x would just be our g of x to the power of 4. So, yes, this is a composite function. So this is the same thing as saying h is following g of x. So let's just recall here to our h of x equals 2x minus 3 to the power of 4. Now, we know how to derive this. We know many rules how to derive a function. And today we're going to learn another rule of how to derive. Now, there's always different ways to deriving, and no way is the wrong way. Some ways may take longer steps, but it doesn't mean that it's wrong. There's always different ways to do something. So let's take the derivative of h of x. So h prime of x is going to be equal to, we bring the 4 down, multiply it by our bracket, so x minus 3. Now we take the exponent, minus 1, so we add to the power of 3, times whatever the derivative of inside the bracket is, so times 2. And this will be equal to 8 times 2x minus 3 to the power of 3. Now what if we looked at this in terms of a composite function? You notice here, this function is very similar to the function that we were looking at over here when we were deciding if it was a composite function or not. So we know it is a composite function. So let's look at it in terms of two functions and then take the derivative of that. So let's look at this and say I have an f at x, which is equal to x to the power of 4, because that's going to be our outside term. And our g of x is going to be equal to 2x minus 3. This here, please note that our x to the power of 4, that really is just saying our g of x to the power of 4. We're going to look at this in terms of u's and y's as we move on in this lesson. But just for the time being, we're going to use this method here. So let's take the derivative of each of these functions. So our f prime of x is going to be equal to 4x cubed. And our g prime of x is just going to be equal to 2. So our h prime of x is going to be our f prime of x times our g prime of x, which really this f is in terms of our g of x because you're replacing that x here in the f with g of x. So really what you're doing is you're taking the derivative of f in terms of g of x here, and then multiplying it by the derivative of g of x. So we can go ahead and put those values in here. So we know that when we take the derivative here, we have 4x cubed times our g prime of x, which is times 2. But we know we have to replace this x here with our g of x. So I know this isn't proper form here. It should be just flowing down the page. But I don't have enough room, so we can multiply that 4 times 2 to give us 8. Now replace that x with our g of x, which is 2x minus 3 to the power of 3. So you notice that when we took the derivative up here and the derivative below, they are the same. So that moves on to our chain rule. So if f and g have derivatives, then h of x is equal to f follows g of x has a derivative, and h prime of x is equal to f prime of g of x times g prime of x. So now let's look at example 1. Differentiate h of x equals x squared plus x all to the power of 3/2. So what we're going to do is we're going to look at this in terms of two different functions because this is another composite function. So let's look at this in terms of our f at x, where I'm going to have my f at x always as my outside term, so my x to the power of 3/2, and our g of x, which is equal to x squared plus x. So that's what's inside the brackets, our inside term. So now let's take the derivative of each. So f prime of x is going to be equal to 3/2 x to the power of 1/2, and our g prime of x is going to be equal to 2x plus 1. So now we're going to use that using the fact that we know what our chain rule is, and we know that our h prime of x is just going to be equal to our f prime of g of x times g prime of x. So we can then sub in here. So we have 3/2 times our x squared plus x, since that's our g of x, all to the power of 1/2, times our g prime of x, which is 2x plus 1. And we don't have to go ahead and expand this at all. Now, another way that I want to look at that is with our using our Leibniz notation here. Okay, so when we're using this notation, we're going to use it and use our terms u and y. Alright, so with our function, so we're going to derive the exact same thing, it's just using a different notation. So with this above, we are going to say that u is equal to x squared plus x. And y in this case is going to be equal to u to the power of 3/2. So our first step here is that we want to take the derivative of u. So we're going to take the derivative of u in terms of x, which we will get 2x plus 1. You'll notice that's the same as when we took the derivative of g prime of x. And similarly, we're going to take the derivative of y in terms of u. So this would be equal to 3/2 u to the power 1/2. Now with the Leibniz notation, what we can do is we have this set up as the derivative of y in terms of dx is going to be equal to the derivative of y in terms of u times the derivative of u in terms of x. So we're just going to put those values in. So we have our 3/2 u to the power of a half times our 2x plus 1. And we know from above here that u is equal to x squared plus x. So we can just sub that value in, and we get 3/2 times x squared plus x to the power of a half times 2x plus 1, which is the exact same derivative of from above. So the chain rule in Leibniz notation, if y is equal to fu, where u is equal to gx, then y is a composite function, and dy, so the derivative of y in terms of u, is equal to dy, so the derivative of y in terms of u, times the derivative of u in terms of x. So example 2, if y is equal to u cubed minus 2u plus 1, where u is equal to 2 times the square root of x, we want to find dy over dx, so the derivative of y in terms of x at x equals 4. So we look at this and we can say right away we know this is Leibniz notation. So recall here that our dy over dx is equal to the derivative of y in terms of u times the derivative of u in terms of x. So let's just do some side work here. We have that y is equal to u cubed minus 2u plus 1, and we have that u is equal to 2 times x to the power of a half. So now let's take the derivative of our composite functions here. So dy over du, so the derivative of y in terms of u is just equal to 3u squared minus 2. And the derivative of u in terms of x is going to be equal to x to the power of negative a half, which we can rewrite that as 1 over root x. Either is correct, but in your end answer, I'd like you to always have a positive exponent. So let's just go ahead and sub in for our derivatives. So we have 3u squared minus 2 times 1 over root x. So let's replace our u there. So we have 3 times, our u is our 2x to the power of a half, all squared, minus 2, and when we multiply, this is all going to be over the root of x. We can therefore go ahead and simplify this a little bit further. So 3 times 2 squared is 4, and x to the power of a half, all squared, is just going to be equal to x. Minus 2, all over root of x. Expand, we get 12x minus 2 all over x. So that is the derivative of y in terms of x. However, we want to find what the derivative is at x equals 4. So the derivative of y in terms of x at x equals 4 is going to be equal to 12 times 4, so we're just subbing in for our x value, minus 2, all over the root of 4, which is equal to 46 divided by 2, and we get 23. So example 3, if y equals x squared minus 5 all to the power of 7, find dy over dx, so the derivative of y in terms of x. So when I look at that, I know the notation already, so I know it's Leibniz notation, so we can go ahead, and I like just to make sure that I'm familiar with the notation and understand what I'm multiplying by. So I always will go ahead and write down the formula there. Okay, you don't have to, it's up to you. So I look at this, I know this is a composite function. So what I'm going to do is I'm going to let u be equal to my inside term, so x squared minus 5. So always let u equal to your inside term, and your outside term let y equal u to the power of 7. Then, second step here, take our derivative. So the derivative of u in terms of x is just going to be equal to 2x, and the derivative of y in terms of u is just equal to 7u to the power of 6. So we can take those derivatives, sub into our formula here, and we get 7u to the power of 6 times our 2x. Now replace that u, multiply the 2 and the 7 to get 14x times our x squared minus 5 all to the power of 6. And there's your derivative. So now let's look at the power of a function rule. If n is a real number and u equals g of x, then the derivative of u to the power of n in terms of x, this is our Leibniz notation here, just so we're aware, is going to be equal to n times u to the power of n minus 1 times the derivative of u in terms of x. Or, if we want to look at the derivative in terms of our g of x to the power of n, which this is our Newton notation, we have n times our function g of x, n minus 1 times g prime of x. Again, they're the exact same, just different notations. So example 6, if y equals f of 3x minus 4, or x to the power of 4, and f prime at 3 equals 4, find the derivative of y in terms of x at x equals 1. So I know that the derivative of y in terms of x is just going to be equal to f prime of g of x. Now I'm using this notation here because of the fact that in the question it gives me f prime and f of 3x to the power of 4. Okay, sorry, let me finish this off. G prime of x. So, looking at this, I know that my g of x is just going to be the value that comes after f. So my g of x is equal to 3x to the power of 4. So let's take the derivative of my g of x. So the derivative of g of x, so g prime of x, is going to be equal to 12x cubed. Now, since I want to know at x equals 1, let's look at what the value of my derivative at 1 is. So I just sub in 1 there, and I get 12. And what about when we have g at 1? So not our derivative, just of g of x at x equals 1. So sub in 1 there, and we just get 3. So let's look at this at x equals 1. So the derivative of y in terms of x is actually just going to be equal to f prime of g at 1 times g prime at 1, which is great because we know those values. So let's see if this will help us. So we have f prime, since our g of 1 is equal to 3, we sub in 3 there. And since our g prime at 1 is equal to 12, we just sub in our 12 there. So then we look at this and we think, well, what is f prime at 3? Well, excellent, because we know from the question that f prime at 3 is equal to 4. So we just sub in 4 there. So 4 times 12, which is equal to 48. And now for our last example, example 7, differentiate y equals the cubed root of x over 1 minus 2x. So again, this is a composite function. I would like to use composite function when I look at something like this. If you can break it up into smaller functions, the easier it is going to be to derive. So I'm going to use my Leibniz notation, so my dy, so the derivative of y in terms of x, which is equal to the derivative of y in terms of u times the derivative of u in terms of x. So I have my u to be my inside term, which is x over 1 minus 2x, and I have my y is going to be equal to the cubed root of u, which I can rewrite that as u to the power of a third. So let's go ahead and take the derivative of both of these. So there's a couple different ways that we can take the derivative of u. You can use your product rule and move that 1 minus 2x up into the numerator position and just apply the negative 1, or you can use the quotient rule. I'm going to go ahead and use the quotient rule. So du over dx, so the derivative of u in terms of x, I first take the derivative of my f at x, so my x here, which is just 1, times 1 minus 2x, minus our f times the derivative of our 1 minus 2x, which is just going to be negative 2, all over my g squared, so 1 minus 2x all squared. So I can go ahead there and expand, so I get 1 minus 2x plus 2x all over 1 minus 2x all squared. So this is just going to be equal to 1 over 1 minus 2x squared. Similarly, I can take the derivative of y in terms of u, which is just going to be equal to a third times u to the power of negative 2/3. So now I can go ahead and put that into my equation here. So this will be equal to a third times u to the power of negative 2/3 times 1 over 1 minus 2x squared. I can replace the u now with my x over 1 minus 2x, so I have a third times x over 1 minus 2x to the power of negative 2/3 times 1 over 1 minus 2x squared. Now, I don't want to deal with the negative fraction there, so what I'm going to do is just flip my fraction. So I have 1 minus 2x all over x to the power of 2/3 times 1 over 1 minus 2x squared. So now I can apply that 2/3 there. So in my numerator position, I'm just going to have 1 minus 2x to the power of 2/3. And in my denominator, I'm going to have 3 times x to the power of 2/3 times 1 minus 2x squared. Since this is all multiplication and division, I can then go ahead and start canceling this brackets out. So 2/3, and what I'll be left with below here is 4/3. So then I can write my final equation, which is just going to be equal to 1 over 3 times x to the power of 2/3 times 1 minus 2x all to the power of 4/3. Now we make sure that we do that because you always need to reduce as much as possible.